Hello, this is Abstract 5181, Training Strategies for Convolutional Neural Networks and Prostate T2 Relaxometry. I'm Patrick Bolin, and my colleagues and I are from the University of Minnesota. This paper is specifically about prostate T2 relaxometry, but this approach can be used for many kinds of quantitative MRI. I have no conflicts to declare. The conventional way to do T2 mapping is to acquire a series of spin echo images with increasing echo times, as shown here, and then you select a single pixel out of this image set, fit it to a curve, and estimate the T2 value, and repeat this for all the pixels in the image to generate a T2 map. In this work, we seek to replace this fitting step with convolutional neural networks which have been trained to encode the mapping between the image set and the T2 map. We'll compare the fitting method with two different CNNs that have been trained to two strategies I'll discuss shortly. But I want to point out that this idea of using CNNs to replace fitting is not novel. There's been a number of papers exploring different aspects of this general strategy, and we detail some of these references in the abstract. The data for this study had been previously acquired in an IRB-approved prospective study of 118 patients with suspected prostate cancer. All of the data were acquired on a Siemens 3T Prisma with an endorectal coil and combined with surface coils. We used a standard multi-echo spin-echo pulse sequence that was provided by the vendor. We used a long TR, an array of TEs from 13 to 145 milliseconds. There's 11 TEs. We discard the first one due to stimulated echo. And these were required at a pretty high in-plane resolution and a 3 millimeter slice thickness. The conventional fitting was done with a nonlinear least squares curve fit. We used SciPy's optimized curve fit with the standard parameters. And we fit the data to a mono-exponential model with two parameters, which are S0, the signal at t equals 0, and the T2 time. And we called the results of this process, this conventional fitting, fit and NLS in the remaining slides. To train the network, we generated synthetic images, which gives essentially unlimited training data and provides an objective ground truth. We used a somewhat novel approach inspired by the AutoMap paper, in which we randomly select photographic images from the ImageNet database. In this example, we took a picture of an elephant and said that's our S0 map, and this picture of a dog is our T2 map. Then we synthesized a multi-echo image series, adding real and imaginary noise and taking the absolute value, and then we generate 10,000 data sets for training and a separate 1,000 data sets for testing. For our network, we used a 2D UNet taken from the Monai library. We used the 10 TE images as input channels, and the output of the network are the S0 and T2 maps. We trained one network in a supervised fashion using the mean square error loss between the true T2 and the estimated T2, and also the true S0 and estimated S0. And we call this network the CNN ImageNet network in our following slides. We trained a second convolutional network using a self-supervised strategy previously proposed for diffusion applications. For this, we use only in vivo data, and we define a data consistency loss function. The model predicts an S0 and a T2 estimate. We use this to synthesize an image series S hats, and then we take the mean square error between the synthesized series and the measured series as a loss function. This model we call the CNN self-supervised in vivo. We'll first look at how these methods perform on synthetic test data. In this example, these maps are the true values. This is the synthetic image series, and this row is the T2 maps predicted with the three methods. You can see that fit NLS gives some noise amplification in the areas where the S0 is low. The self-supervised method does a little better, and the CNN ImageNet does the best job at estimating T2 in these low SNR areas. Since we know the true T2 values, we can measure the actual errors, and this plot shows the mean absolute error over all 1,000 samples in the test data set. You can see that CNN ImageNet gives the lowest mean absolute error with the lowest variation of all the three methods. We can also look at how the error depends on signal to noise on a per pixel basis. In these three plots, you can see that the three methods, at high SNR, they all give very low bias. But in the low SNR regime, the top two methods overestimate T2, whereas CNN and ImageNet shows little bias and small variation. Here's an example from the in vivo test set. Qualitatively, all three methods produce reasonable T2 maps, except for some artifacts in the rectum area, which is essentially the background region. If you compare the actual values in the prostate, the high signal to noise area, all the methods agree quite well. But in the low SNR regions, like the muscle as shown here, you can see that this CNN SS in vivo agrees with fit and LLS, but CNN ImageNet gives lower values than the other two methods. This is consistent with the overestimation of T2 we saw in the synthetic data set. We can see the same effect if we retrospectively add noise to the data. This top row shows all three methods on a different in vivo case, and then in the lower rows we add noise to the data. And you can see that the fit results, these two columns, show increasing T2 values as the data get noisier. They become more yellow, whereas CNN ImageNet gives consistent T2 maps even in very noisy data. So in this study, we saw that the fitting method and the self-supervised CNN gave errors at low SNR, primarily because they don't fit the Riccian noise well. CNN ImageNet, in contrast, gave unbiased T2 estimates and provided some denoising, and potentially because of this, gives more accurate values in vivo. It does have some downsides, causing some blurring, and is sensitive to the training distributions, which wasn't shown here. In summary, we showed that a CNN trained with synthetic data in a supervised manner can give lower errors and better noise robustness than nonlinear least squares fitting or the self-supervised approach. And we think this method can be applied to many other quantitative MR techniques. Thank you.